Good morning, Happy New Year, and welcome to season 16 of Chai and Why. Today is, if our counting is right, episode 397. And thank you all for coming over the years. We hope to provide you some equally engaging, interesting discussions about science and its connections to everyday life and everything else. It's a pleasure to welcome Basudev Dasgupta, who will do today's session. But before that, since there are I see a lot of new faces, maybe just a word that Chai and Why happens on the first Sunday of every month here at Prithvi Theatre, on the third Sunday of every month at Ruparel College in Matunga. If a month has a fifth Sunday, it's a session that's live from a lab at the IFR, that's online only. And we are trying our best to also be online, at least the talk part of it. So that's how it is. The next session here will most likely be on mathematics. Again, we're not completely sure, but the announcement should be up in a day or two. The session coming up immediately, the mid-January session at Ruparel, is about optical spectroscopy, about how materials are interrogated with light to try and find out things about them, and in particular, light and magnetic fields together. That is used to find information about mostly semiconducting materials. We're going to have that 15 days from now, and a month from now, we'll be back here. Okay. So to introduce Basu, who's going to tell us about chance, I suppose, today. He did his PhD from TIFR itself, and then he went postdocing around the world and eventually came back to us. He's in the Department of Theoretical Physics. He works on what I think is called astroparticle physics. And this is his second Chai and Why. He was here in sometime in 2015 telling us about dark matter. But today it's a more livelier topic, I suppose, not so dark, on chance. And I'm going to hand it over then to you. Remember, if you have questions, you can always ask, or you can wait till the end and ask. It's up to you. Online audience, we can only see your questions via chat. So please put your questions and comments in the chat box, and we will take them appropriately. Okay.
Should we start?
Yeah.
Okay.
Are you ready?
Right.
Okay.
So thank you for having me. So we're trying to do a little experiment today. It's not a usual talk. We have tried to integrate my presentation into a very amateur skit. So please indulge us. This is also our first time. We don't know how well we'll do, but let's try and have some fun. Okay. All right. Win or loss, जीत या हार, पास या फेल, क्यों है चांस, क्या है चांस, why are things not predictable? पॉकेट में पैसा डालते हैं, गायब तो नहीं हो जाता। तो ऐसा कैसे होता है कि किया वही पर रिजल्ट अलग अलग, टॉस किया कॉइन, कभी हेड कभी टेल, ऐसा क्यों? न्यूटन ने बताया है, जो भी इनिशियल कंडीशंस हम सेट कर देते हैं, फिर न्यूटन्स लॉज के हिसाब से एक ही उत्तर आना चाहिए। अलग अलग कैसे हो सकता है? बहुत पेचीदा सवाल है कि नहीं? और फिर ये सारे रैंडमनेस में से क्या कभी कोई ऑर्डर आ सकता है? हमारी जिंदगी तो बिखर जाएगी अगर सिर्फ रैंडमनेस के बलबूते पे हम चलेंगे। कैसे चल रही है ये दुनिया इतने रैंडमनेस के बावजूद? सोचने वाली बात है कि नहीं?
Order, order, order. I am order. The meticulous planner of the universe. The architect of certainty. And most important, my laws give predictability.
Hello, और मैं हूँ random, the unexpected, the unpredictable, and the essence of chance.
I bring structure to the universe, structure to chaos.
और मैं लगाती हूँ आपके boring predictable life में chance का तड़का. After all, What is life without a little bit of unpredictability?
Array, how can there be randomness when the laws of physics predict all trajectories? Exactly, madam. The laws of physics are universal. The laws of physics dictate how every particle moves.
It's not about laws. It's about inaccuracy. And inaccuracy leads to unpredictability. क्या ज्ञान गुरु आप ही समझाइए.
हाँ, मैं समझाता हूँ.
Okay. So, all right. So now the more serious scientific part of the thing. All right. Indulge us a little bit. We're not theater professionals, but you can't resist the urge to do a little bit of theater when you're on this stage. Okay. All right. Thank you for having me again. I'll tell you a little bit about chance. It's about probability. Chance is another name for probability. So probability is all around us. Okay. So you think that sometimes probability is just some subject that you learn in school or in college, in some textbook, but it is not like that. It's all around us. It affects every little action, that we do and that's done to us in our lives. So just to start off, all physical processes have a little bit of randomness built into them. So at the level of classical mechanics, which is the Newton's laws, you must have heard many talks here already. You are a very educated audience, I'm quite sure, and I've been told so. So particles like atoms, they move, but even if we think of classical mechanics, yes.
For some reason, the screen share is showing the presenter view to the outside.
Okay, let me fix that.
Regular.
So, okay, we're going to do that. Yes, tell me. Slideshow. Use slideshow, I think. But yeah. All right. Thank you very much. Okay. So as I was telling you, Okay, I think this is good, right? Is this fine? All right. So as I was telling you, probability is all around us. It's in the basic laws of physics. I'll tell you a little bit more about it. Chemical reactions only happen when you mix things very well. There is an element of probability and randomness there. Biological processes are random. Even identical twins, they are not exactly identical. So something has changed. Same mother, same father, almost the same conditions, but very different people. But forget about these, very scientific sounding things. Even the more practical things that happen to us in our day-to-day lives, like our finances. If any of you has ever put money in the stock market, you know what randomness is, what chance is. Okay, we've been through a period of turmoil in our society with so much of discussion about public health. COVID happened. So, and in all of that, there was an element of probability, because you have to always think that if I go and attend a talk at the Prithvi Theatre, where there will be, let's say 50 other people, what are the increased chances that I am acquiring the COVID? This was a calculation that you were implicitly doing. That's the reason why people were not going to crowded places or staying homes. If you are old or if you are very young, you have to account for that extra probability of falling sick, and you take actions according to that. Not only that, a very important aspect of our lives is our electoral democracy. We vote. Every 5 years, we really have to worry about who's going to win, and every single one of us is voting with some intuitive calculation in our heads as to what's the effect of this one single vote that I cast and what impact it has on our country. So you see, probability and chance, these things have entered every little bit of our lives. We don't think about it often, but it plays a very important role. In fact, I would go to the extent of saying that whoever we are, wherever we are, we owe a big portion of our current status or position in life to chance. A sequence of lucky events can take us to a very favorable position. A sequence of unfortunate events can take us to a very unpleasant place. And so we should be aware of the huge impact that probability plays in our lives. So what I am going to do today is I'm going to tell you what is probability. I'm trying to define it a little bit more precisely, and I'll try to explain where it comes from. Like, why is there such a thing called probability? You're aware that such a thing is there, but why is it there? And I hope this question will make sense later on. Okay, so there are two definitions of probability. I will use this definition, which is that probability is the frequency of occurrence of something. Okay, so this is the definition, frequency of occurrence. So let's give an example. The most famous example when it comes to probability is that what happens when you toss a coin. Okay, so I have a 10 rupee coin here. Okay, so this is the heads. Okay, this is the tails. Okay, so now I don't look at it before I start tossing. I don't know whether it's head or tails on top. I hold my coin like this and I toss. Okay, now can you tell me whether it's head or tails on top? No. Head. Well, you're right. There you go. Okay. So somebody is lucky. All right. Put some money in the stock market today. All right. So but you see, sometimes when I do the same thing, and now is it head or tail? It's still head. Oh. There you go. So sometimes we don't get it right. So why is this happening? I will try to explain to that. But first, we define probability. The definition is that I toss this coin many times, let's say 1 million times. And I count how many times I got head. Let's say if I toss this coin many times, what I can show experimentally, I do this experiment, is that as I make the number of tosses very large, the number of times I get heads for a fair coin is exactly half of the number of tosses. So then I say that the probability of heads is half. Similarly, I can do for tails, and the tails would be the other half. Okay, we ignore cases where the coin stands on the edge or things like that. We also ignore cases where somebody is cheating, where the coin has two heads on both sides, or it's an unfair coin for some reason. So for now, simple case, fair coin, we say that we toss it many times, count the number of times we get heads, and number of times we get heads is NH divided by total number of times capital N. We call that probability of heads. Okay, so that's the definition of probability. What's the second example? We all have seen dice, Ludo khelte hum. So that dice has 6 faces. The faces have 1, 2, 3, 4, 5, 6 written on them. You roll them and you ask what is the probability of any one of the faces. Let's say the size that has 3 dots. Okay, and the answer is that I roll it many times. I say 1 million. What I really mean is as big a number as you can do. Okay, as big a number as you can do. You roll it 1 million times and you will find that 1/6 roughly of the times you get any one of the faces if the dice is fair, not Shakuni's dice. All right. Now, but you see, these are textbook examples. These you study in some book. If you are in class 11th and 12th in math, you read these things. But let's take a slightly more useful example. What is the probability that any one of us, let's say, madam, has vitamin D deficiency? We don't know, right, a priori, but we can try to make a guess. So, assuming that all of us roughly belong to a similar population biologically, that we have the same diet, same working habits, same amount of sun exposure and so on, same genetics, roughly that is true here. What I can do is I can take a survey. I can test everybody else for vitamin D. So let's say there are 100 people here, and I test, and I find that 20 of you have vitamin D deficiency. Then I can guess that madam will have vitamin D deficiency with a probability of how much? 20 divided by 100. That is 0.2. So this is a way that statisticians use to make decisions in society. If you want to guess how likely is somebody to have some disease, you do a survey, you do statistics, and you make guesses like this. So that's a definition of probability. All right. So ये तो हुआ कि what is probability? Just to make sure that we are all on the same page. But the next question is, why is probability? Now, does this question make sense? Is anyone actually, already convinced that no, of course probability has to be there? Do any of you have strong opinions about, of course probability is there?
Yeah, because multiple outcomes are possible, right?
Yeah.
So how do I know if only a certain outcome will come?
How?
I know that multiple are possible.
So question was that, are you sure or not sure that there should be something called probability? And sir is saying that, well, if something has multiple outcomes, how can you be sure which outcome will happen? That's the answer. But you see, would you agree that this is not necessarily the only way to think? Newton says that for any given situation, if you tell me where you start, there are equations that I can solve, and it tells the final answer. So how can there be multiple outcomes? That is actually the point, that how there can be multiple outcomes to the same starting point. Start exactly the same way, but you have multiple outcomes. I start with my coin and I, do something. How is it that I don't know whether it will be head or tail? It should be completely predictable.
And that is part of the equation.
Well, if you are a physicist, you actually believe that they are. That's the thing. That's so it's actually a valid point. The objection is that who told you that you solve equations and you predict? If you really are a physicist and you believe in the way physics works, you see that we can predict lots of things. In fact, that's the most beautiful part of science, that we learn to predict the future. It's actually like magic. Tell me. Good. So we'll come to that. Thank you. You are extremely foresighted. Of course, perhaps you have been helped a little bit by Miss Random, but we will come to that. So what we will, excellent. So the answer was that yes, there is predictability, given some initial conditions and the equations of physics, somehow we can predict the final answer. But we don't know the initial conditions perfectly. And we can't solve everything perfectly. We don't measure everything perfectly. This imperfection will lead to multiple outcomes. We will make this point very precise. Yes, you have one more question.
I thought of you an example of this, like what I was saying.
Yes.
Example, like he detected, astronomer detected fluctuations in Mercury's orbit. It's called a flux when you can see the gravity. But later when relativity and I can see the gravity.
Yeah, but I but I don't think this is directly related to what we are talking, no? I mean, this is important stuff, but it is always true that sometimes we don't know enough about the world. Like, so our laws of physics are also constantly being improved upon. But that's not the kind of inaccuracy that we are talking about right now. Assume for now that we know the laws perfectly, and we'll talk about it more in detail. Okay? Even then, there are inaccuracies, and that's what leads to multiple outcomes. So what I'm trying to explain in the next 15 minutes is why there are multiple outcomes from apparently similar initial conditions. The question is clear to everyone? Okay, good. All right. So this is what we've been saying, that the world basically runs according to the laws of physics, and these laws are fully deterministic. Deterministic meaning that if the starting conditions are same, the final conditions are predicted and same. So imagine that you think of the starting conditions as some point, and then you solve the equations, and this point flows and ends at some other point. And this point is some really complicated system with many parameters, and it describes where you are, what your weight is, what your height is, what the temperature in the room at that point is, and so on. It can contain any amount of information. All of this is represented by a single point, and as time evolves, you reach some other point, but this evolution is completely predicted by laws of physics. And yet we are saying that this does not happen. Why? So there are actually three causes for probability. The first cause is something called chaos. Chaos in classical laws of Newton itself, which says that it is true that given a point, we can tell its future. But take two very nearby points, very, very nearby, as near as you like. Their futures do not have to be close enough. Their futures can diverge. This is a property of the Newton's laws already. That tells you that if you don't measure the initial conditions absolutely, infinitely precisely, in the end, you will not be able to predict. Because if you miss even by the slightest bit here, you forget whether you are here or here, right? This is called chaos. The second source of uncertainty is quantum mechanics. This is, of course, familiar to many of you. I will not go into too much detail, which basically says that, well, you can't actually predict the position and the velocity of a particle at any time. So you can't say where it will end up. There is a fundamental uncertainty in the initial conditions in that way. But what I will try to argue in the next 10 minutes or so is that these two things are not really the dominant source of probability in our lives. Neither chaos nor quantum mechanics are the real reason for probability. For example, for this coin has nothing to do with quantum mechanics, right? Because, like, if that were the case, this coin would suddenly reappear there. That does not happen. This coin obeys purely the laws of Newton. And there is no sensitive initial conditions here. As I will show you in detail. There is a third reason for probability, and which is where most of the randomness in our lives come from, and that is a limited accuracy of measurements. Now, this might already start making a little bit of sense, but I will make this more concrete over the next 7-8 minutes. Okay, so chaos as a source of probability is basically this picture. That suppose you have a pencil, it's standing on its tip. It will fall in some direction, but depending on exactly which direction it was leaning in to begin with, it will fall in that direction. Oops. Okay. All right. It will fall in that direction. So as you can, it says that even if you're like 1/10,000th of an atom away from the vertical, within 3 seconds, a 10-centimeter long pencil just falls. But it falls in the direction in which it was initially leaning. So even if you're off by, to the left or to the right by a little bit, your outcomes are very different, whether you fall to the left or to the right. This is chaos. Okay, this is actually instability. The second kind of uncertainty, as I said, is something to do with quantum mechanics, that you have an electron coming out of some electron gun, it can go through two of these holes in some wall, and it ends up on this screen. Unlike bullets, which would either go through this hole or this hole and make two spots here, when you send electrons to this, what you get is something that looks like this. You can see that there are these, sort of multiple blobs that appear. This is called an interference pattern. You might have heard about it. And this is an indication that you can't predict where the electron will end up. What has happened here is that I have emitted many, many electrons, and finally I have collected the heat map of all the electrons where they have ended up, right? So it tells you that I can't predict to begin with that they will end up here and here. If the electron goes through this window, it comes here. If it goes through this window, it comes here. That's not the case. And that's because of quantum mechanics, because this electron is not going like this and like this. The electron is a cloud, and it goes through everything all at once. It interferes with itself, and probabilistically it can end up anywhere. So that's quantum mechanics. But as I said, the randomness of this coin has nothing to do with either that chaos or this quantum mechanics. So what is happening? Okay, so here is the answer. See, when we toss a coin, see what is happening. When we toss the coin like this, I am doing two things. I am throwing the coin upwards. There's a speed that's going upward, and that speed is what keeps it in air for some time t. If the speed is more, it stays in the air for longer. If it's less, it stays in the air for less. Within that time, I'm also giving it some spin. So it's flipping like this. If it spends more time in the air and it has some spin, it takes more number of rotations. For a given time, if I start with a very small spin, so if I do like this, it does not flip at all. So there are two things that I'm controlling: how much spin I give and what speed I launch. So it turns out that I can actually solve this problem completely. There is no uncertainty, there is no randomness here. So if we give it an upward speed v and a spin w, as I write, the time it spends in the air is this velocity divided by acceleration due to gravity, 9.8 meters per second square, right? This is taught in class 7, right? And then if you know the time and you know the rotations per second, you multiply the spin by the time and you get the number of rotations. That's n flip. If this n flip is even, it comes back exactly where you started. If it's odd, you change from heads to tails, right? So solve the problem completely. Where is the randomness? There's no randomness. Okay, so let's see what's happening. So here is a picture where on this horizontal axis, I have the upward speed in meters per second. Why are the numbers like 1, 2, 3, 4, 5 meters per second? Because notice this. When I toss a coin, it spends how much time in the air roughly? About 1, 2 seconds. But yeah, roughly 5 seconds is not a bad. I have to toss a bit higher. I have to be very good at it. But roughly 1 to 2 seconds. So if 9.8 meters per second square is the acceleration due to gravity, and it's spending about 1 or 2 seconds, you can quickly calculate that the speed that I must have given is around 2-3 meters per second. Very easy to. And you notice, you see how fast it's spinning. It's about 20, 30, 40 times per second, per minute, right? Sorry, I have written it wrong. Should be per minute. Okay. So 20 revolutions per minute is per second is very fast. That's not what's happening, but 20 per minute. Okay. So anyway, so on this space, every toss is 1 point, right? So if I toss with very high speed, but very little spin, it is here. If I toss with a very low speed, ऐसे थोड़ा सा ऐसे किया, कितना भी spin दे दो, it's over here, right? Generally, we are tossing somewhere over here. Just to, make things a bit clearer, here is a bigger coin. So there is heads. Okay, everyone can see this. So what I'm saying is that if I toss with no spin, okay, with no spin, but high speed, that's a bit like this. Okay, no flips. If I toss with no speed up, but a spin, it basically does not flip again, right? Even if I give a lot of spin, it will get stuck, right? Everyone can see. So if I give a lot of spin, but no upward velocity, it does not flip. Only a combination of speed and spin will make it flip many, many times. So it's very clear that for some region of spin and speeds, it does not flip. And above that line, it flips once or more. Okay, you can actually calculate that line given the equations that I did. But not only that, if I now increase my speed or spin a little bit away from this line, from here, it will spin 2 times. Okay? Everyone with me so far? Imagine now, this is no flips, this is one flip. Suppose I start with heads. What does this tell me? No flips, meaning that it turns up heads. One flip is it turns tails. Completely predictable. So if I know what my V and W is, heads, tails, and so on. Actually, therefore, I can just completely solve this problem and tell you that if you are here, it's tails, if you are here, it is heads, and so on. The full space of V and W tells you by tossing a coin. And in fact, this is the reason why if I do a toss like this, you don't consider that a fair toss. Why? Because this toss, this very bad toss, is when we are here. Very low speed, very low spin. I can control the toss. And I know perfectly that I will turn up exactly the 1/2 flip, right? So if I give low speed and low spin, I control the toss. There is no randomness. Okay. However, most fair tosses like this are here. You give it a very large spin. Okay. Now, when you are here, what's happening? Within my uncertainty of the initial velocity and the initial spin, there are stripes of heads and tails, and I don't know if I am exactly here or here or here or where. I am in that yellow box. I know that. But in that yellow box are both heads and tails almost equally. So what do we get? So we get a probability of 50%. So I wanted to get you to this point of precisely realizing how uncertainty in the initial measurement of speed and spin leads to the probability of 50% for a coin. Are you all convinced that this is what's happening? Okay, we're all together. Okay. So now this is the moral of the first part of our talk, is that why is there probability? Because of imprecision in initial measurements. Okay. So with that, I will take your leave. Okay. Well, all right. Let's go on.
We have built a machine that can reproduce quickly in parts the same spin and velocity.
Yeah.
Will that converge? Say I know the starting state of the quantum all these.
Yes. Yes. People have done that.
Another context, suppose you do it on Mars, it's different.
But G is different, but you can calculate it there. Yeah.
The air drag also.
So of course, that's a very good point. the question was that what will happen if you go to can you actually do this very reliably if you have a robot that launches it very predictably? And the answer is yes. People have done these experiments and they can predict coin tosses if you do that. Second question was that what happens if you go to Mars? Answer is basically the same thing, but G is different. Third comment was that what about air drag and such things? Actually, this problem is much more complicated. In fact, you have to include air drag, but even more than air drag, what happens is that when you flip the coin like this, it doesn't just flip. It also does some complicated motion like this. It's called precession. You have to include that. And in fact, this treatment that I just showed you is something from a paper by a professor at Stanford, Percy Diaconis. He used to be a magician's assistant. It's a very interesting character. And so Percy Diaconis wrote a paper showing that actually coins don't have 50-50 probability. It's around 0.51 and 0.49 in favor of the face that starts on the top. So this is a little, monetary benefit that I can give you all before you. If ever asked to call a toss, as long as it's a fair toss, call the face that's up top. You have approximately a 1% advantage by doing so. If someone hides it, you can't do it. That's why people hide it. That's why people hide it. Because otherwise you have a 1%, advantage. Okay. Any other questions?
No, but I am order and chaos cannot prevail over order.
See, even in the most precise plan, chaos will disrupt.
No. This cannot happen. How can chaos prevail? नहीं तो इस पृथ्वी में ये अर्थ में अनर्थ हो जाएगा.
Push again.
Chaos cannot prevail.
Actually, बात अलग है. See, when there are multiple random variables, they cancel each other out. So now we will tell you about that. यही तो interesting बात है. Each variable is random, but the sum of random variables is less random. Counterintuitive बात है, पर सच है. दिखाते हैं हम आपको.
Yes, please.
Give us a minute.
Yeah, that's fine. All right. I think we are back to more scientific style of delivery, less theatrics. But I hope you're enjoying yourselves. Okay, good. All right. So we also need to have something fun to do. It gets boring to keep talking like this. All right.
Ever think so much about talking about?
Chalo. So now I'm going to try to explain to you that although each coin toss is completely random, right? I mean, okay, random with 1% advantage, but so on, but basically random, right? 50-50. But we already started by saying this, that if I toss the coin 100 times, 1000 times, I can predict the fraction of the times it's heads, right? That was practically the definition of probability. So if I make a bet with you, okay, 100 rupees bet, you have to predict head or tails. A very risky bet. You might win, you might lose, you don't feel comfortable. But if I tell you a different thing, if I say that, okay, I will toss a coin 100 times, okay, and you have to tell me the number of times it will be head, and I will allow you a leeway of plus or minus 5. Normally you would guess 50, but even if it is between 45 and 55, I will give it to you. Do you feel like taking this bet? Yes. You feel like taking this bet. You feel that you will win, right? If I tell you that I will toss this coin 1000 times, right? And 500 times roughly it should come head and tails, but I will give you a leeway of another 10%, let's say. So 50 plus, so 450 plus 550. Would you take this bet? Yes. Would you take this bet preferentially to 45 and 55? Yes. All of you understand this intuitively. I want to make it more precise. Okay? This is the point. What is happening? That many random variables on average cancel the randomness out. ऐसा नहीं है कि randomness keeps adding. So normally खाने में नमक के बाद नमक मिलाते जाएंगे तो ज्यादा नमकीन हो जाता है, चीनी पे चीनी मिलाते जाओ तो ज्यादा मीठा हो जाएगा, पर यहाँ पे रैंडमनेस मिलाओ तो कम रैंडम होता है. Very different thing, right? Okay, so each coin is random, but the fraction of heads becomes closer to half as n is large. We've already said that. On-time performance of a flight or train. You know, we've all been traveling. When you get on a flight or a train, and I ask you to predict कि late होगा या नहीं होगा, बता सकते हो? बहुत मुश्किल है बता. It gets very difficult sometimes. You know, that's why it's so frustrating, right? But on the other hand, if you have seen that a particular train or a particular flight has a propensity to be late, वो हमेशा late ही होता है. हम लोग कहते हैं ना, कह रहे हैं इस पे मत जाओ, ये तो हमेशा late होता है ये flight, right? Especially late night flights, because the exactly. Thank you, sir. Last flight always late, right? Why? Because all the delays add up. But therefore, we can predictably say that it will be late, right? So similarly, there are other examples where we can say that randomness will add up, but in a way that it cancels each other. So, okay, so this is an example. What I am showing you is the fraction of times I get heads. You know, in 10 tosses, I toss the coin 10 times, right? If I toss the coin 10 times, roughly I should get 50%, half of the time head. But if I do this experiment of tossing 10 times, 100 times, you know, basically imagine that 100 of us are here. Each of us has tossed a coin 10 times and calculated कि क्या fraction आया मेरे को, right? ऐसा नहीं है कि everybody will get half. Some people will get 0.2, some people will get 0.8 and even higher. Most of us will get around 0.5. But notice something, that although this is very peaked around 0.5, it's very broad. Why is it broad? Because I am only tossing 10 times. Okay. If each of us tosses the coin 30 times, so I have done all these experiments and I'm just showing you the results of these experiments. Okay. Then you see, none of us is getting a fraction of 0.2 anymore. Nobody is getting 80% heads. We are all between 30 to 70% roughly. Still not 50%. Error hai, uncertainty hai, but getting closer with 30 tosses. With 100 tosses, things are beginning to look good, right? Now, if I take this bet with you, to predict the fraction of heads to within 0.1, 0.5 plus or minus 0.1, with 100 tosses, I think you will almost 100% take the bet, right? Because almost guaranteed hai ki I will be able to predict. With 1,000 tosses, this is what happens. I'm sorry? I can't hear you. Burj Khalifa. Yes. Very much so. So, what is happening is that as number of trials is increasing, I am getting the correct average probability and I am getting it more precisely. My chance of being off from the true value is becoming less and less. Clear? Okay. So, why does this happen? The reason this happens has something to do with a theorem in mathematics called the central limit theorem. In that theorem, you can prove that as you add many random numbers which are drawn identically and independently. इसका मतलब क्या है कि for example head or tails, each toss is independent of each other and the coin is not changing, nothing is changing. So every time, whether I get head or tails, my initial setup is the same. That is the meaning of identically distributed, that prepared identically. And independent means that I don't do anything different based on the previous toss. ऐसा नहीं है कि पिछली बार head आया so I put the head on top, or I change my velocity or do something else. Every toss is totally independent. So at least in that case, one can prove mathematically that the sum of random numbers converges to the initial mean. 50-50 था तो वो 50-50 के पास जाएगा, and the variance, यानी कि the noise away from that mean, the chance that you will not actually get exactly the predicted probability, that decreases as 1 divided by square root of the number of times that you toss. 1 over square root n. This is very important, square root n. So if, for example, you want to reduce this width by a factor of 10, the number of times you have to toss is not 10 times more. It's how many times more? It's 100 times more. Okay, so in the stock market, if you want to reduce your error, in some prediction for, let's say, making money on some mutual fund, in order to reduce the error by factor of 2, somehow you have to increase the number of observations by a factor of 4. This is something that's actually used by companies, financial companies that do quantitative financial management. They know how to combine many stocks to make sure that the volatility of any one mutual fund is much lower than the individual stocks. इसीलिए लोग कहते हैं ना कि mutual funds are less risky than individual stocks. This is the logic behind it. Now I'll come back to it in a bit. Okay. So this is a little problem for you. We will discuss this after the talk if there is interest. But suppose there is a big drum. Yes.
The bet that you gave, the case of how you bet.
Yes, if somebody offers you, you should choose as large a number as possible. Indeed. Yeah, but if somebody gives you a choice between 30 and 100 and 1000, you always choose 1000. But whether you will choose a bet or not depends on the width that you know. So you can calculate that. And somebody tells you that, okay, I will allow plus or minus 0.1, versus somebody tells you I will allow plus or minus 0.05. You have to know which one will work in your favor. Okay.
The larger number, if they offer it shorter.
There you go. So, yes.
So I, at the graph of 100 steps, there was this outlier.
Yes.
What is playing here?
It just happens. Random extreme fluctuations also happens. Okay. The question is that why is there this point, and there's nothing in between? This is the nature of noise. Noise does not say that things will always be smooth and predictable. This happens. Yes. Yes, this is regression to this feature, that by taking lots of data, you come closer and closer to the mean, is called in common language regression to the mean. Okay. I will come to this again a bit later, but one misconception is that because this happens, and a lot of events have happened, let's say on this side, you take कि अरे next वाला इधर आएगा, right? वो गलत है, वो नहीं है. That is not guaranteed at all, because you are predicted to come to the mean after very large number of trials, and always many trials are left. So the very next one you don't know where it will be. So that is a wrong idea कि अगर बहुत loss हुआ है तो अगला profit आएगा. नहीं होता ऐसा. Okay?
Because I know what you're saying, but intuitively, if you are crossing 1,000 times,
yes,
fair point, and you have 999 edge.
Okay.
There's a voice in your head which goes.
Very good.
To
very good. Very good. Can we hold on to that question for after the chai? This is a very good question. The question was कि अगर एक coin को 100 बार टॉस किया और 99 बार हेड आया, is everything that I have told you, you should disbelieve. And I will come back to this. This is a very important point, but it's a slight departure from the thing that I'm trying to talk about. This has to do with more different definition of probability than I have told you. It's called Bayesian, but we'll come back to that after the chai. Huh? But let me proceed now. Yeah. Okay, so it turns out that the distribution of sample means follows the central limit distribution or the normal distribution as given by the central limit theorem. That is true, indeed. Yes. Okay, so I told you why does this happen? Because of central limit theorem, which actually tells you that the distribution of means, this shape that you see is what is known as the bell curve or the Gaussian distribution or the normal distribution. There is a name. Okay, it's very universal. And anyway, so I was going to say that there is a problem that I want to assign to all of you. Being a professor, you can't help but give homework. Okay, but this is a fun homework, I hope, because this is actually, tell you whether you have understood the point. Suppose there's a big drum, with red and white balls. You don't know how many of each. Okay, and I ask you, what you are allowed to do is you are allowed to take one ball, look at it, put it back, shake the drum again, take another, and put it back. You do it as many times as you want, and tell me what is the fraction of red and white balls in this drum. This is the problem. Huh? Clear है problem? बड़ा drum है. Not, you can't see opaque drum. Many balls inside, tennis balls, let's say, red and white. You are allowed to take one out at a time, look at it, put it back, shake the drum, take another, and so on. I want to know the fraction of red and white balls in this drum at the end. How many times will you look in order to tell me this probability to about, let's say, with an error of at most 10%? So let's say agar 50-50 hai, correct me. So you should be able to tell me between 0.49 and 0.51. इस accuracy पे मुझे probability बताना है. Okay, 1% या 10%, whatever is the answer. How many times do I need to look? This is the question. Okay, so this question I will not answer. Think about it. Okay, but I will give you some gyan now. Okay, this is very important because all this fun and games, this must lead to something. So 2 more slides. One is my advice to all of you, that what you should do if you are a scientist. Okay, if you are a scientist or you are doing anything that requires measurements and numbers, you must measure several times and take average. This was known to our great ancestors who said, measure twice, cut once. Okay, so Darjis know this better than others. Please measure things twice, at least thrice, I would say. Okay, why? Because the measurement mein jo error hai, wo average karne pe it will become less. Not only that, don't ever, in any scientific setting, say that the answer is 123.1. That answer actually makes no sense. Say it is 123.1 with an uncertainty of 0.1 or 0.2 or what. You must quote the uncertainty when you quote a result. Without quoting the uncertainty, the result has no meaning. If I say that my answer is 5, but I don't tell you that I have an uncertainty of 25, what does that 5 mean? It means nothing. It could be 0. It could be 50. Right? So so that is the reason why science is different from math. In math, answers are a number. In science, answers are a range. All scientific results must be quoted as a range. So the middle value plus or minus the uncertainty. This was my second advice. And as a result, there is no point in quoting numbers to arbitrary number of decimal places. कोई अगर पूछे मेरा weight कितना है, 70.127489, makes no sense. क्योंकि जिससे मैं measure कर रहा हूँ, that itself has a least count of 100 grams. Between that, it can't tell. So I should say my weight is 70 kilos plus or minus 0.1. Okay, this is how numbers need to be quoted to be believable and scientific. Okay, and this is the last point. If 2 results are compatible within their uncertainties. So 69 and 70 seem different. But if both of them have an error of 1 or 0.5 even, 69.5 and 70 minus 0.5 become roughly the same. You should not think that they are different. This will bring us to the last point that I want to make. This last slide was mainly for scientists, but this slide is for everyone. Okay, everyone who lives in society in some serious way. Now we have understood that the results of all experiments and observations are subject to uncertainty. Subject to market risk, subject to uncertainty. Okay. So important decisions that you make in your life. You are comparing reviews of 2 things on Amazon. 7,000 रिव्यू है 4.4 स्टार है, 6,000 रिव्यू है और उसका 4.1 स्टार है, और 3 रिव्यू है और 5 स्टार है. We understand not to trust that 5-star, 3 5-star review, right? We intuitively know this. What is behind this intuition? That the uncertainty on that 5-star reviews is very large. Don't think of that as better than the 4.3-star review with 7,000 reviews. Abhi reviews biased hai, wo baat alag hai. But all things considered, understand that mean values mean nothing if the uncertainties are large. So somebody tells you कि हाँ मेरा ये whatever दवाई है इसका efficacy is 87%, उस दवाई का 83%, उस दवाई का 79%. You say हाँ 83% ज्यादा है. What is the error? How many people did the test? That is what determines whether 83% is actually different from 73%. If that information is not provided, you should not trust, or at least you should not make big decisions based on that. Again, financial markets. Somebody tells that my profit, whatever XIRR was 13.447%. Go and check. Is it better than everything else statistically? Or within errors, everything is equal to Nifty 50. Right? Don't trust just because somebody has the larger mean. Uncertainty agar zyada hua, so that's a problem. Okay? And then finally, if we learn to use this judgment, we can distinguish genuine claims, medicine works, an investment is profitable, a medical intervention, mask pehna is useful or not useful. All of these important decisions can be therefore understood from this statistical perspective, from this perspective of chance. Okay, so that's the end of my presentation. Thank you all. Thank you very much. हाँ ओके, अभी ऑर्डर आ गया है तो चलिए हम चाय पीते हैं.
Alright, chai time, folks. And please come back after chai. I'm sure you have got a question. There are answers to these puzzles as well.
Did you?
Yes.
Oh, like it's lots of
No, on the computer.
He's asking some questions. That's why we have to solve them. And
Thank you.
I get my 10 rupees back, which is very good.
Caution money चाहिए.
Well, there's a big coin there as well. Yes, come back. Online audience, if you have questions, this is your time. Last chance, put them in the comment and we will try and answer them.
Small question. How does one decide the sample size? How many times should the...
So the question is, how many times should we do an experiment? How do we decide the size of the sample? And the answer is the accuracy that we require. If I want 10% accuracy, 1 over square root n basically tells me that I need to do 100 tosses. 100 ka square root will be 10, so 1 over square root n will be 0.1. So if I need 10% accuracy, 0.1 ka accuracy, I need 100 samples at least. So that's the rough rule of thumb. Yes. Yes. It doesn't matter how big the drum is. Yes.
So what did you say?
Okay, so let's